Okay. All right. Thank you.
Yeah, so thank you very much. So my name is Nick Rivera. I'm a PhD student at MIT. And today what I want to talk to you about is recent work in devising new types of nonlinear phenomena to control the statistics and fluctuations of light. As Charles had mentioned, many of us are fascinated by the fundamentals. That's what got us into science. I've been long fascinated by the fundamentals of light. And I've long believed that in order to get at those fundamentals, we need to be able to understand light quantum mechanically and to control it quantum mechanically. And that's where nonlinear optics and nonlinear physics becomes really interesting, because it's the main tool that we have to create quantum states of light that have no classical analog. And the one that I want to focus on today are Fock states of the electromagnetic field. So as Charles had mentioned, this is in collaboration with some of my MIT collaborators, as well as Guido Kaminer at the Technion. And so without further ado, let me get started. So this talk is about Fock states of the radiation field. They're fundamental, they're important, and they're very, very hard to produce. I'm going to keep the discussion simple. Instead of thinking about a Fock state of say a multi-mode field, I want to think about just a Fock state of a single mode of the electromagnetic field. You might think about a Fock state propagating inside a cavity formed by two mirrors. Now, the Fock states are, in a way, the most fundamental states of the quantized radiation field of photons, because we know that, say, a single mode of the electromagnetic field can be associated with a simple harmonic oscillator. And so its Hamiltonian is something like, can you guys see my cursor, just out of curiosity?
Yes, we can. Yes.
Okay, great. So the Hamiltonian of a simple harmonic oscillator is something like A dagger A, where A is the annihilation operator, A dagger is the creation operator. And so these Fock states are just states with a definite number of excitations. In the position basis, they have these types of wave functions that we're all very familiar with. And Fock states have very interesting statistical properties. Of course, a Fock state with n photons has exactly n photons. It never has any probability of having anything but n photons, so the mean is n and the variance is 0. Now, the Fock state is also a little bit similar to the vacuum state of the electromagnetic field, in the sense that it has no mean values of its electric or magnetic fields, but it does have a finite variance, which is actually the 0-point value multiplied by 2n plus 1. So it's basically scaling the photon fluctuations without having a mean field associated with it. Now, the fact that these are the energy eigenstates of the field, and thus the most fundamental from the quantum mechanical perspective, already is enough to want to be able to produce them for arbitrary values of n. Yet they also are really exciting from an application perspective as well. For example, from metrology and spectroscopy perspective, the fact that there's no number or intensity noise in these fields is interesting for having for doing measurements with noise which is below the classical shot noise limit associated with coherent states of the electromagnetic field, or classical light, like what you generally produce from, for example, from a laser. It's also interesting from a quantum computation and quantum simulation perspective. People have used relatively small, say 10 photon microwave Fock states and encoded information into them. So they could take these Fock states, do some kinds of manipulations, read out the final state, and then use it to, say, solve the problem of what is the spectrum of the rotational energy spectrum of a molecule. So they have other uses too. From the fundamental perspective, the reason we got excited about them, besides them being the most basic state of light, is that they have no classical counterpart whatsoever. For example, if you try and represent a Fock state as a phase space distribution, your phase space function will inevitably be negative, which means that this phase space doesn't represent a probability per se. And there's a theorem in quantum optics that tells you that those states cannot be produced classically by superposing a bunch of different current sources in a classical way. Also, because they're the basis states of the electromagnetic field, they're also a workhorse for generating other quantum mechanical states. And finally, the other thing I find exciting about them is that if you could produce a Fock state with, say, thousands or tens of thousands or millions of photons, it would represent basically a macroscopic quantum state in much the same way that something like a Bose-Einstein condensate or a superconductor, which is a Bose-Einstein condensate of Cooper pairs, is a macroscopic quantum state. So, okay, that was like 12 reasons why these are really interesting. And now let me get to the other part, which is that they're very hard to produce. One is that, light matter interactions are governed by the interaction Hamiltonian between the field and matter. So if I want to produce light, it needs to interact with matter. The typical form of the interaction is like dipole dot field. And there's very little in that Hamiltonian that naturally selects in the Fock basis. So there aren't that many physical mechanisms that just want to produce Fock states. And the other important thing is that even if you produce this thing, it's fragile in the presence of loss. And the reason is simple. Suppose I have n photons in my cavity, but one of my cavity mirrors is partially transmitting. Then probabilistic, every time the photons bounce around, photons will randomly leak out at undetermined times. If they're leaking out at undetermined times, then the instantaneous probability distribution for a certain number of photons is going to spread out over time. And so loss tends to degrade these things, as they do many other quantum states. So it's not all completely hopeless. Fock states can be generated both in microwave and optical frequencies, but with clear limitations. So at microwave frequencies, it's possible to build Fock states of, say, 10 to 15 photons. And the idea is that basically using cavity quantum electrodynamical interactions between things like superconducting qubits, which form the matter, and an LC resonator, which forms the light or the cavity, you can basically apply arbitrary sequence of pulses or well-determined sequences of pulses to the superconducting qubit to enforce it to add a photon at exactly determined times so that you have a Fock state at certain times. And you can build up this Fock state one by one until your cavity losses set in, and that's what sets this current limit of about 10 to 15 photons. At optical frequencies, we don't have that kind of facility over cavity quantum electrodynamical interactions yet. And so the main workhorse for generating Fock states, say single photon Fock states, is heralded spontaneous parametric down conversion. So in other words, we send a pump into a, say, chi2 or second order nonlinear crystal. A photon splits into two. We measure one that heralds the other and generates a single photon Fock state. The parametric down conversion process by itself does not produce two photon Fock states because the process isn't perfectly efficient, and so therefore it's inevitably mixed with the vacuum. You can also produce Fock states by collapsing the system in the number basis and making a number resolved measurement. But under those circumstances, your Fock states are non-deterministic. Sometimes it will have one photon, sometimes it will have three, and the probability that it has more than this is typically quite low. So this problem of generating Fock states, especially in optics, is quite acute. And it's part of a larger problem of how you generate arbitrary quantum mechanical states of light at macroscopic scales. The main way that we have to do this, as I had mentioned in my introduction, is through nonlinear optics. Nonlinear optics allows us to generate these non-classical states of radiation because it introduces terms into the electromagnetic field Hamiltonian, which are non-quadratic. For example, if I have a chi2 nonlinearity, it's going to add a term to the energy, which is like the electric field cubed, which is in contrast to the free electromagnetic field, which is like E squared plus B squared. And so these cubic terms basically allow for us to go beyond classical states of light in a fairly simple way. So it allows for phenomena like spontaneous parametric down conversion, squeezing, four-wave mixing, and all that kind of stuff. And so nonlinearity can come from things like these nonlinear crystals, but it can also come from it can sort of be synthetic. Like in this microwave example I showed, where people use superconducting qubits to generate photons one at a time, those strong cavity quantum electrodynamical interactions between the qubit and the cavity are a form of nonlinearity, which is operable at single photon scale. So it's a very strong type of nonlinearity. And as I mentioned in optics, we don't have too much of that. But using these kinds of second and third order nonlinearities and strong coupling, we know how to generate squeeze states, we know how to generate single photons. But the main question is, how do you make a nonlinearity that wants to produce a large Fock state? That's still a question that needs to be answered, and that's what the results I want to show you address. Just to kind of foreshadow a little bit, let's just think about what we would want from a nonlinearity that produces exactly n photons, or in other words, an n photon Fock state. And to do that, let me start with an analogy, which is the phenomenon of photon blockade in quantum optics. So suppose we have a qubit placed inside a cavity, and this qubit is interacting with the cavity. The dipole of the qubit is coupled to the field of the cavity. And suppose that the cavity and the qubit are on resonance. Well, if the loss of the cavity is small enough, then the qubit and the cavity will strongly couple. And so the degeneracy between the qubit transition and the cavity transition will split. And so this degeneracy splitting is strong coupling, and the states associated with that degeneracy splitting are polaritons. So it's actually much better illustrated in this picture here. So in the absence of any coupling between the matter and the field, I have the ground state. I have the ground state with one photon, the excited state with zero photon are degenerate. I have that the excited state with one photon and the ground state with two photons are degenerate. But then with the coupling, those different states split in energy to form these lower and upper polariton states. And the important thing is that the splitting between the upper and lower polariton states depends on how many photons were in the state originally. So this splitting is like 2G, but this one is like 2G root 2, and the next one would be like 2G root 3. And so this leads to the phenomenon of photon blockade. In particular, imagine I send in a stream of photons, which is resonant with a transition from 0 to 1+. Well, because it's resonant and there's no non-zero matrix element, you expect that transition to occur efficiently between 0 and 1 plus. But now, let's imagine that a second photon wants to come into the cavity. Well, it can't excite it to 2 plus because actually now the energy doesn't work anymore. You see the blue is now taking you above the 2 plus state. And so therefore the second photon that comes in has to bounce off. And this is photon blockade. You can only have one excitation at a time in the cavity. Now for a Fock state, it would be really nice if we had something like an n photon blockade where the system was letting you put in n photons, but not letting you put in n plus 1, or alternatively, given n photons, you couldn't go to n minus 1. So this is the kind of phenomenon that would solve our problem, but strong coupling itself doesn't do this. But with that, I now want to kind of get into the meat of the results and show you what we're thinking about and the way that we want to produce Fock states. So I'm going to focus particularly on the case of producing Fock states in optics. We also looked at ways to produce very large Fock states in the microwave regime as well. I won't have enough time to talk about that, I think, today, but there is another paper on that, so I'll direct you to it at the end if I remember to. So yeah, let's talk about optical nonlinearities in preparation of macroscopic optical Fock states. So this work is on the archive, as Charles had mentioned. Identifiers right here if you want to take a look at it. So in this work, we basically propose a few schemes for producing macroscopic optical Fock states and introduce a few new physical principles that should facilitate that. And so I like to present it as something that occurs in 2 steps. So in the first step of this proposal, I'm going to show you a special kind of nonlinear intensity-dependent dissipation. So dissipation can just mean simple leakage of photons. So if we think back to the cavity formed by 2 mirrors and we think of photons bouncing around, I'm going to need a situation where the rate at which photons leave the cavity depends on the number of photons in the cavity in some special way. The statement is that if this happens in just the right way, then in time, a state that has photons in it will decay into a Fock state and produce a Fock state or a close sub-Poissonian approximation transiently. I should mention that in cases where we don't produce Fock states, it's still possible to produce light where the number is much more well-defined than it would be for shot noise or for coherent light from an ideal laser. And we call those kinds of states sub-Poissonian light, and more mathematically, their variance is less than their mean. So basically, we're going to, in step 1, we construct the special nonlinear dissipation that allows for transient generation of Fock or sub-Poissonian approximations. And then in the second state, we're going to stabilize those states in time and convert them into steady states of the system by incorporating a gain medium that interacts with this special nonlinear intensity-dependent dissipation. In other words, we're going to think about constructing lasers that saturate not only due to gain saturation, but due to this new nonlinear dissipation mechanism. And we've been coining this kind of laser as the Fock laser because the steady state solution of the master equation becomes a Fock state or a close sub-Poissonian approximation thereof. So with that, now let's start by discussing step 1, which is this special nonlinear intensity-dependent dissipation. So the phrase I like to coin is dissipative preparation of large Fock states. And so the starting point is to think about the decay of light in a cavity with an embedded nonlinear medium. And at this stage, the nonlinear medium is somewhat magical. And then in a few slides, I'll discuss how you actually go about this. The effect of the nonlinear medium is going to be to induce this intensity-dependent dissipation that I mentioned. And in order to understand what kind of intensity-dependent dissipation is needed, we need to understand the effect of dissipation on the probability distribution for photons in the cavity. So I'm going to introduce this quantity P of n, which is the probability that the cavity has n photons. For a Fock state, P of n is going to be a Kronecker delta function. It will be 1 for some photon number n naught, and then 0 for all other photon numbers. And for coherent light, it would be something like the Poisson distribution, and sub-Poissonian light would be somewhere in between the Poisson distribution and the Kronecker delta. So the effect of dissipation on the probability distribution is as follows. The probability of having n photons is going to leak away because n photons in the cavity can transition to n minus 1 when a photon leaks out the cavity. So there will be a term minus Pn with decaying with rate Ln. But there will also be positive contributions to the probability of n photons, because if you have n plus 1 and 1 leaks out, well, now you have n photons. So probability feeds into P of n, into n from n plus 1. And these are really just the rates of absorption from n plus 1 to n, or n to n minus 1. And so now I've transferred the problem to saying what is the form of L of n that I need in order to get some kind of Fock state. And so pictorially, it's shown here. So in this plot, I'm showing the loss coefficient, which is L of n divided by n. That's basically the temporal decay coefficient for light in the cavity. And I'm plotting it as a function of the photon number. Now, let's ignore this crazy shape for a second. Let me just tell you what's normal. If you have so-called linear loss, where the loss is independent of intensity, as many of the cases that we consider in most problems, then this plot would just be a horizontal line. So that's the linear loss case. And with linear loss, if you have something like a Poisson distribution of photons initially, it's going to decay and stay Poissonian. But I want to introduce a loss that instead looks something like this. It's got this crazy non-monotonic shape, and more important, and well, also just as importantly, it has a zero. It's a magic photon number, which I'm going to call N naught, because that's basically going to be the Fock state index. And then away from N naught, the loss sharply rises. And so to see how this is, now let's think about what happens if I start with, say, some kind of distribution of light, say the Poisson distribution at some initial time t naught, and then I let it go in this loss landscape. Well, because there's only loss in the system, the photon probability distribution is going to decay. Now, so that means it's going to move to the left towards lower photon numbers. Now, as it moves towards the left, it's going to reach this region that here, where it's going to fall through a region of sharply rising loss. And when I say sharply rising, I mean reading from left to right. So it sharply rises as N increases. And the claim, one of the important physical effects that we report in this paper is that when the probability distribution falls through a region of sharply rising loss, the noise condenses. In other words, the probability distribution gets tighter. And if it initially starts Poissonian, it'll become sub-Poissonian. And the way to see that, the simplest way to see that, is to look at the equation of motion for the first two cumulants. One is the mean, the other is the variance. So the mean decays according to the average rate of loss. That's to be expected. The variance decays according to, is influenced by two contributions. One is a decaying contribution, proportional to delta n squared. So you might imagine, well, if I have a Poisson distribution and it decays into another Poisson distribution of less photons, the variance has to decrease. So this negative term is responsible for that. And dLdn would just be kappa, a constant temporal loss coefficient for the linear loss case. But fluctuation dissipation makes you think, well, if I have loss, then fluctuations probably should be fed in. And that's exactly what this positive L of n term does. So the variance evolves according to two contributions. However, L of n and dLdn are in principle independent. So consider the following situation. Imagine dLdn is sufficiently large so that this negative term overtakes this term. That's exactly what happens in this region of sharp rising loss. Well, in that case, you're going to have that the variance drops below the mean, and if the variance was equal to the mean at first, and you'll have something that becomes sub-Poissonian. Now, the second part of this story is what happens when, as this distribution is falling, it hits N0. Well, if at N naught, there's no loss, the probability distribution has no way whatsoever to move to lower photon numbers. Therefore, it's going to stay stuck. So the parts of the probability distribution above N naught will continue to move towards N naught, but the part at N naught is not allowed to go anywhere. Therefore, you've created this kind of trapping potential for the photon probability distribution, and the ultimate result is a Fock state as time goes to infinity. And so this is the kind of mechanism that's responsible for it. And now I want to address somewhat how you create such a thing. And so the way to create a nonlinear loss of this type goes as follows. And I'll justify this with a rigorous theory in the next slide. So let's imagine that we have our cavity again. There's these two mirrors, and one of the mirrors, I'm just going to consider it as perfectly reflecting to make the discussion simple and frequency independent. So one of my mirrors is perfectly reflecting, and the other is frequency dependent. It has a frequency dependent transmission coefficient. And we might imagine that it has a frequency dependent transmission coefficient like this. This is a phono line shape, for example. And now, besides these two mirrors, I also have a nonlinear medium inside, which is a Kerr nonlinear medium, whose index changes as a function of the number of photons inside the cavity due to the Kerr effect. So for example, if the index of refraction changes, the resonant frequency of the cavity changes. And so, for example, here in the second plot, this is the resonance frequency of some cavity mode as a function of the photon number in the cavity. So as the number of photons increases, the cavity resonance frequency decreases. And so now you might imagine, well, okay, my transmission, which is like my loss, depends on frequency. My frequency depends on photon number. So I have a loss that depends on photon number, which is just the composition of these two functions and looks something like this. Now this holds under the limit where basically the frequency dependent mirror has a really fast response time. So it's responding to the instantaneous cavity frequency, basically adiabatically. So there's lights bouncing around and its intensity is changing. Well, its apparent frequency to the mirror is changing, and therefore the loss changes. So that's kind of the physical picture of what's going on. And now let me just tell you how we came about actually showing that this is right, because this intuition is rather simple. We wanted to explicitly construct this kind of loss coefficient from a microscopic model of a cavity with a nonlinear medium and one frequency dependent mirror. And so what we formulated a Hamiltonian, which basically has the minimal elements needed to display this phenomenon. So we considered a case where you have one resonance A, that's kind of like the cavity resonance, and then a resonance which represents the mirror mode. And both the cavity and the mirror mode are coupled to the same continuum of far field modes on the left side. So they can couple to a continuum, and then the mirror on the right is just perfectly reflecting as before. So the continuum on the right is not important in this problem. And then we also have the nonlinear medium, which makes the Hamiltonian of A anharmonic. So the overall Hamiltonian of this system, well, there's the Hamiltonian of the cavity A, which is going to have a linear part, A dagger A, and a nonlinear part, which for a Kerr Hamiltonian is like A dagger A squared. And then you have the Hamiltonian of the mirror. I'm not going to put a nonlinear medium in it, but could. So the Hamiltonian will just be linear. And then, well, D can in principle couple to A, so we allow a term for that. But most importantly is the reservoir. So we have the reservoir, which is a continuum of propagating modes, which can come from either direction. And so we have a sum over all reservoir modes, and then we have a coupling of the cavity to the reservoir modes, and we have a coupling of D to those same reservoir modes. And because of that, it allows for the possibility of interference, because A basically has, if we just thought about A alone, it basically has two channels to leak out onto the left-hand side, into the left continuum. It could pass directly into the continuum, or it could pass through D and then go to the continuum, and those two channels can interfere, like in the Fano effect. And so to show that kind of effect, what we did is we looked at the equation of motion for the two modes, A and D, tracing out the effect of the reservoir, because this is an open quantum system, and we don't really want to follow the dynamics of the reservoir. And so we get a type of master equation. We have the first term here, which represents the conservative part of the evolution of A and D, basically the energy conservative part. But then we also have a part, which is a Lindblad operator, which dictates the leakage of photons in A and D into the continuum. And the important thing, the thing that differs from standard treatments of loss, is that normally if you just have a single resonance mode and it has some decay, well, the jump operator, which dictates that decay, would just be proportional to A. But here it's a sum of a contribution of A and one from D, which reflects the fact that you can have interference on the way into the continuum. And so one thing I mentioned is that, the intuition we had for why this stuff works is in the adiabatic limit, where the response time of the D mode is actually quite short. And therefore, D is responding to the instantaneous field A, and we can eliminate D from the equations of motion and just get an equation for the A mode. So we can write an equation for the density matrix. It's quite complicated. It's much more complicated than your standard master equation for linear loss. It just reflects how nonlinear dissipation works. And the reason I show it to you here is because it gives us a rigorous formulation of not only how the probability distributions of photons in A will evolve, and that's what I can use this equation to do, but it also tells us how field and intensity and higher order field correlations evolve due to this nonlinear dissipation. So it also tells us about its impact on G1, G2, and so on. I won't get into that. I will just stick to analyzing the probability distributions in this talk, but I just wanted to point out that this is, in a sense, a key foundational result for this work. So let's look at the equation of motion just for the diagonal components of the density matrix, which are the probabilities. So rho nn is just P of n. And you immediately find that P of n evolves in the way that I pointed out before, where there's an intensity-dependent loss. L of n is n times this thing, and this thing is the intensity-dependent temporal loss coefficient. So it's the thing that's plotted in red here from before. And you can see that it has some dependence on n, and in particular, that dependence is through the detuning between the A mode and the D mode. In other words, you might imagine the following. You might imagine that because, okay, so A here can leak into the continuum, which is this, either directly or through D. Now, so there are two amplitudes that tell you the overall rate at which A is going into the far field. Or into the continuum. And you might imagine that those relative interference amplitudes actually depend on, the detuning between A and D. And so in particular, what's happening here is that, well, the interference amplitudes depend on depend on the detuning, but the detuning depends on the photon number in A. So whether you have constructive or destructive interference depends on the number of photons in A. And that's exactly what this kind of form of the temporal loss coefficient is saying. And in particular, let me show you something. So let's consider the case where lambda is 0. Well, if lambda is 0, then I just have this first term in the numerator, kappa delta of n squared. So if, as light is leaking out, the A frequency matches the D frequency for some photon number n naught, the system becomes lossless. This interference becomes perfectly destructive. And so that'll set my n naught. So that's just to explain that this is basically a nonlinear interference effect. And it actually has a similar flavor to phenomena like electromagnetically induced transparency, where as a function of some parameter, two leakage pathways can interfere and the system can become transparent. In a way, this is very much like what's happening here, but here it's all with photons. So now I've described kind of the physical intuition, the framework we use to get at it, kind of proved the main results. But now I want to show you what it looks like a little bit more. So I want to show you examples. So let's consider what happens to photon probability distributions in a sort of realistic example. So here I'm going to consider a case where I have some nonlinearity. The nonlinearity I'm going to use is fairly strong. It's characteristic of some of the recent work people have been doing on exciton polaritons in coupling quantum wells to Bragg mirrors. I'm going to assume that this nonlinearity coincides with, is basically formed by the strong coupling of a quantum well to a cavity. The cavity has one perfectly reflective mirror and one frequency dependent mirror like a phonomirror. And that's going to lead to an intensity dependent loss coefficient, temporal loss coefficient, which looks something like this. So it's going to have a 0 for n naught of about 1,000. And I'm going to consider how the photon probability distributions evolve under two different initial conditions. So this plot's a little bit misplaced because we should really look at the bottom panels first. So in the bottom panel, in the bottom two panels, I consider the case where my initial photon distribution is something like a Poisson distribution with 800 photons. 800 is less than n naught, which means that the photon probability distribution will not fall through a region of sharply rising loss. So you'd actually expect the fluctuations to increase. And then eventually, once it falls through a region where loss is effectively constant, then it will become something like Poissonian. And so here in the second panel, I'm showing snapshots of the probability distribution, P of n, for different times. So this is the original time, T naught, and then there are these times here, 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 and here. And so as time evolves, well, for the first time I show, the distribution actually spreads out. It actually becomes somewhat super Poissonian, which means it becomes more noisy. And then it starts to condense. It actually condenses to a Poisson distribution, but the mean number is tending to 0. Now, this is a little bit easier to see on the plot on the right, where I'm plotting the mean and the variance as a function of time. So you can see that the y scale is log and the x scale is linear. So you see that the blue, well, it's like a line. So photon number is basically exponentially decaying, as you might expect. And then the variance first jumps way above the mean. That's basically what's happening from the blue to the orange curve in the middle panel. And then it falls and then basically reaches the Poisson level as the photon number decays to 0. This is a pretty stark contrast with what happens in the top two panels. Here I consider an initial condition where I have a Poisson distribution centered at around 1,200 photons, and then I let it go. And you're seeing that it's tightening as a function of time, and it's condensing, it's becoming tighter and tighter around 1,000 photons, which is n naught. And this P of n, and basically as time goes to infinity, P of nt turns into this Fock state with exactly 1,000 photons. And if you look at the mean and variance, you see that the mean, well, okay, that's basically going from 1,200 to 1,000, so it barely changes. And then the variance is decaying way faster than the mean and tending to 0. So this is exactly the effect I was describing, just shown for an example of where you have nonlinearities and frequency-dependent mirrors, which are somewhat realistic. One thing I should point out is that this effect is limited by having finite linear loss at n naught. So if my loss isn't exactly 0 at n naught because I have some finite linear loss, well, then the noise reduction is going to decrease and I won't have a Fock state. I'll have a sub-Poissonian approximation. But in practice, if you can reduce the noise by like 90 or 95%, then you will become pretty sub-Poissonian, like 90 or 95% below the shot noise limit. And so I think there's quite some prospects for observing these kinds of effects. Now, because of this linear loss, in all real cases, these states will be transient. It will eventually, the probability distribution will blow through n naught and eventually go to 0. So I would like to stabilize these kinds of states in time. And so with that kind of motivation, we thought about we thought about the following question. What if I just introduce a gain medium into this system in order to basically stabilize the state in an equilibrium between this nonlinear loss and gain? And, there's quite a few questions you can ask about that, because gain is known to introduce various fluctuations and noises and complications. So it's important, we did have to rigorously think about this kind of stuff and formulate a theory. But now let me just kind of get to it. So basically, this kind of nonlinear loss is the backbone for a kind of laser that emits Fock states or sub-Poissonian approximations once you introduce a gain medium. So let's consider the system from before: two resonances coupled to the same continuum, and then a gain medium put inside the resonance with the nonlinearity. And so basically, now what will happen is that I don't have to start from a state with initial photons to generate a Fock state. Before, I had to start with over 1,000 photons in order to get to an 1,000 photon Fock state. Here, I can in principle build the state up from vacuum, because once the gain exceeds the loss at 0 photons, well, then photons will start to build up by stimulated emission, and then I can get to an equilibrium point with low loss. So that's the basic idea here. And so this is, panel A is like the spatial representation of the system, or the physical representation, but it's also important to think a little bit about where energy goes. So, this system basically is composed of a gain medium interacting with a nonlinear cavity through stimulated emission and absorption. The gain medium has energy coming into it and fluctuations from a pump. It also has energy leaving and fluctuations added through decay of the polarization and the inversion associated with T2 and T1 times. And the cavity also has some dissipation, and this dissipation is going to be exactly of the type described before, this kind of nonlinear dissipation. And so this type of nonlinear interaction enables a new kind of laser that emits Fock states. And so let me kind of explain the principle here. So a really useful way for us to conceptualize these things is with these kinds of gain loss diagrams that I'm showing here. And so what I'm plotting is the gain coefficient and the loss coefficient as a function of photon number for a few different cases. We can focus on the left panel first, which is the so-called conventional laser case, where my gain is saturable gain and my loss is linear loss. So the loss is a horizontal line, and saturable gain has this kind of 1/n-like behavior for large n. And so we know that in a laser, the operating point is basically where the gain balances the loss. So on this curve, it's where the two curves, the green and red curves intersect. And so that tells you something about the mean number of photons. But these curves actually also tell you something about the fluctuations in the number of photons as well. And what we found from our theory is that the fluctuations in the number of photons has to do with the angle at which the green and red curves cross each other at the equilibrium point. So in particular, the steeper this intersection is, the less fluctuations you have and the closer to a Fock state you become. And so let me explain to you how we understand this. So the idea is, the way we think of it's like this. The system, the system steady state is where gain balances loss. Now, if you have a fluctuation in the photon number from that point, you're operating at a place where gain doesn't balance loss because you've moved either to the right or the left on this curve. Presumably, the system does not really want to be in a place where the gain is very different from the loss, or vice versa. So for example, if I'm on the high photon number side, well, you would think fluctuations leak back. And if I'm on the low number side, photons will get amplified to the steady state. So I should have a low probability for large deviations. But if I have a steep angle of crossing between the two curves, the gain loss differential increases more rapidly for the same photon number. And so you'd expect a small fluctuation to be accompanied by a large gain loss differential, and therefore a low probability of that state occurring. And so basically, under those circumstances, the photon number probability distribution for the photon is going to get compressed below the Poisson level that you expect for an ideal laser. And when this gets more extreme, you tend to a Fock state. And so this is, in this middle panel, I'm showing what happens when you have saturable gain and the kind of sharp loss we've been discussing. But one corollary of this kind of logic is that if you have a sharply decreasing gain at the equilibrium point, the same thing is going to happen. And so this is another way to do it. But I've mostly focused on sharp loss because in photonics, and especially nanophotonics, we have a lot of ways to engineer loss, and it's a lot more controllable than many gain media. So I think sharp loss is definitely the first way this will get realized, but someone might prove me wrong. So let me now come to analyze a little bit what are the characteristics of an optical Fock laser. So let me just start with kind of like, well, how does the pump of the gain medium translate to the number of photons in the cavity in the steady state? So on the y-axis, I'm showing these gain loss curves in this plot. I'm showing many gain curves in one loss curve. The loss is red. And then the gain curves are the blue, the various green curves, and the black curve, which all correspond to different levels of pumping of a gain medium. And so now let me look at the lowest level of pumping, which is this blue curve here. So this blue curve is below threshold. If you start with 0 photons, the gain is less than the loss. The system has no reason to build up photons and go towards a steady state. I mean, the steady state is just going to be 0 photons. Then the system will be in something like a thermal state. Now, once the gain at 0 photons exceeds the loss at 0 photons, now I'm above threshold. The stimulated emission will occur until I hit a steady state. And so, for example, with this dash dot curve here, I have some steady state at this photon number. Now, the interesting thing there's a few interesting things about this system. I think the way I'll start is let's talk about what happens when you have a large pump relative to threshold. So it's this curve up here where I'm at 3 times the threshold. Well, you have this steep intersection with the red curve, and so basically when you start with 0 photons, you'll move to this point, and this point has pretty low loss. It's something like 95% below the coherent state level, so it's quite quantum mechanical. But it turns out that you can see it here that actually some of these curves actually intersect the loss. Some of these gain curves intersect the loss twice or intersect in funny ways. So actually, for example, maybe I'll focus on, the dash dot here. The dash dot curve has one intersection here and one intersection here. It actually has 2 stable steady states. And so you might imagine there's some notion of bistability here, and my initial conditions will dictate whether I hit this point, which has fairly high noise, or this point, which has fairly low noise. Even the below threshold curves actually have a stable equilibrium as shown in this inset here. And so you might imagine that if I start from high pump and then lower, then I can reach this low noise state, which actually has way more than 99% less noise than the coherent state level. And so, just from these gain loss curves alone, we can already start to imagine some pretty interesting output characteristics. So here, for example, I show the mean number of photons as a function of pump. And you can see, well, there's basically 2 curves because there's 2 steady states in some places. So there's the purple and there's the blue. Let's focus on the purple curve first because it's much closer to the behavior of a conventional laser. So the purple curve, I have 0 photons in the cavity until I hit a threshold. Then my number of photons increases basically linearly. So if this was a conventional laser, it would follow the gray dashed line. But instead, it's following this purple curve. And this point here corresponds to the black curve on the previous slide where the steady state discontinuously changes. So the S curve for this system will start with 0, follow somewhat linearly, and then jump to this blue branch and then go to some low noise states. Now, if I start from the blue branch with high pumping and then lower, and then I lower to 0, and I stay at this other steady state, I will actually approach a Fock state exactly. And so that's quite interesting. This is also illustrated here in these panels of the mean and variance. Probably the easiest thing to look at is the variance divided by the mean. So when that's above 1, it's super Poissonian. When it's less than 1, it's sub Poissonian, and 0 for a Fock state. So for the purple branch, I'm always stuck being super Poissonian. You can also see that here. For the blue branch, once I either jump to it or follow it from above, the noise is significantly less than the coherent state level. In all cases, for all parameters in this plot, it's below 90% of the coherent state level. And we can also understand this analytically. It turns out that the uncertainty of photons in the steady state is basically like the loss derivative divided, so it's like the loss sharpness divided by the loss to the -1/2 power. So if the loss is really sharp, this becomes small, or if the loss is somewhat sharp, but this is basically 0, this also becomes small. And so it's exactly the same effect that I was describing without the gain medium, but now the state is stabilized in time. And so the last thing I want to discuss is, can this effect also be realized in sort of conventional laser architectures, maybe under some kind of unusual design scenarios? And so we, oh, sorry, Siri. So that, the short answer is that this is in principle possible, and I want to show you kind of what that would look like. So we were kind of thinking, well, could I do the following? Could I have a cavity which is 4 by 1, say perfectly reflective mirror, and one of these magic mirrors with frequency dependent transmission with a curve medium with weak nonlinearity, and a gain medium, something like a solid state gain medium with 4 level atoms inside, which is optically pumped, which could reduce the noise below the coherent state level or produce Fock states. And the short answer is that it would be hard to produce Fock states with the system. That is no surprise, but it is possible to produce heavily sub-Quaternion states according to the exact same mechanism that I'm describing. And so here, what I'm showing are those kinds of results. So here for this system, I'm showing the gain loss curves for different levels of pumping. This is the pump magnitude in, say, kilowatts per square centimeter. The one thing I should point out is that this is under some unusual design constraints because it requires an extremely high finesse cavity to start, something on the order of 10,000 or so. Which is of course possible, but it's not standard for a laser. But supposing you have this nonlinear medium in the gain, then we have the same kind of biostability and low noise states as before. And in fact, say for the case where you have a single steady state with low noise, you can have noise which is, say, 80% less than the shot noise limit in this kind of conventional laser architecture. And here I'm talking about like a few millimeter scale laser with a solid state gain medium in it. And in this kind of bistable regime where you have two steady states, the noise can be over 90% less than the shot noise limit. And these are all states with something like 10 to the 12 photons. So these are extremely macroscopic states with very low noise. And I think that's very exciting. I think there's quite a lot of room to improve on this. This is kind of the first, theoretical isolation and design. I'm sure there are better ways to do this. And I bet many of you have very good ideas on how to proceed. And I think what's really exciting about this is that all of this is a consequence of nonlinear dissipation. And dissipation and nonlinearity are something that people are really intensely focusing on these days, especially in my native field of nanophotonics, where people can engineer loss using phonal resonances, effects like bound states in the continuum, using things like photonic crystals and other kinds of complicated nanoscale geometries. And we're also starting to have much more control over nonlinear systems, boosting nonlinear efficiencies with nanoscale resonators, and using strong coupling and other types of effects. This is nicely summarized in a lot of, this is considered a lot in these kinds of fields of non-Hermitian optics and also phonal resonances and bound states in the continuum. So I think there's a lot of opportunities for systems to explore. I think there's a lot of even richer effects than what was shown here. And I hope that this can provide an exciting starting point. And we're starting to validate some of these ideas in the lab, building systems with nonlinear dissipation and looking at their quantum noise. And so with that, I want to thank Charles for the invitation and then take some questions and discussion.
Yeah, great. Thank you very much, Nick. I want to open it up to if anyone has any questions. I think that was a really wonderful talk. When you talk about deep, strong coupling versus just strong coupling, what is the contrast there? I didn't quite understand.
Wait a minute. Which slide are you referring to, by the way?
Well, no, I'm just, from reading your paper. Yeah, you're talking about deep, strong coupling.
Yeah. Okay. So this is great. I had additional slides on this topic. So that's the second paper. This Fock lasing based on deep, strong coupling of light and matter, which is also on the archive. So I believe that's what you're referring to. So yeah, what I discussed was basically the optical version, which doesn't use any deep, strong coupling, but it's possible to build large Fock states in microwave using deep, strong coupling. Embarrassingly, I had the audacity to think that I could cover both of these topics in one talk, and then I practiced and found out that I could not. I'm close. So deep, strong coupling. The idea is this. Suppose that we have a qubit coupled to a cavity. So and I'll use the standard description. So the qubit has its own energy, h bar omega over 2 sigma z. The cavity has its own energy, and then there's a coupling between them, which couples the dipole of the qubit to the field of the cavity with some coupling constant g. Now, in strong coupling, we refer to cases where the coupling is larger than the loss in the system, which means that the degeneracy splitting associated with the polaritonic states here is actually resolvable. So when the coupling exceeds the loss, you can resolve this energy, these splittings, and then you have these polaritonic states that are well defined. So deep strong coupling refers to something quite more aggressive in a sense. It refers to the case where the coupling is stronger than the natural frequencies of the qubit and the oscillator. So that's a much more stringent condition. So for example, strong coupling, well, if your cavity quality factor is 1,000,000, then your coupling only needs to be 1 part in 10 to the 6 of the natural frequency. Deep strong coupling, the cavity would have to be the coupling would have to be larger than the natural frequency. So that did not happen for a very long time. I'm pulling this plot from a Reviews of Modern Physics, where the coupling normalized to the frequency is plotted as a function of time. And this represents 1 here. And this is quite recent. So there were 2 papers in 2017, both using superconducting qubits that realized this deep strong coupling. And the idea, the thing that's really beautiful, actually, we found this out before we did the optics work, but then we started to think about what you'd need to do in optics. So the cool thing about deep strong coupling is that if you ask what are the energy levels of the hybrid states, and for very strong coupling, they're harmonic. So here I'm plotting the energy spectrum, or the energy levels, as a function of coupling strength. And so you can see, okay, so for weak coupling, I have this kind of polaritonic energy level structure, and then for stronger couplings, I have the definitely non-harmonic ladder. But then for stronger couplings, it starts to look harmonic and evenly spaced again, except it's only evenly spaced up to a point. And then it starts to become unevenly spaced again. That point is when you have about g² number of photons. So if the dimensionless coupling is 5, then you start to become anharmonic at 25 photons. And so this system is linear up to 25 and extremely nonlinear beyond 25. And so if you imagine pumping that system, you imagine that you might only be able to create a Fock state of 25 photons, because your stimulated emission is normal for the first number of photons. Here it's for 100, and then it becomes 0. And so you have this kind of sharp gain, which intersects linear loss to produce a Fock state. So that's the idea.
I see. Yeah, thank you. That helps me very much.
What is the frequency? What is the wavelength of the photons typically?
In these deep strong coupling scenarios, we're talking about a few gigahertz. So that's some number of millimeters. And for the optics stuff, we were really talking about the near infrared.
Okay, and what is the size of the cavities typically?
Yeah, so that depends on the architecture. So for example, here I illustrate a case where the cavity is a few millimeters in length. It can also be done with it being larger than that. And in this exciton polariton situation, I was using parameters from the paper on exciton polaritons, where they use a cavity of about 1 or 2 microns formed by 2 Bragg mirrors. So pretty large free spectral range.
Now you do this, of course, in the laboratory with actual physical stuff. Is that correct?
Well, that's what we're doing now. So right now, what I'm illustrating is kind of the theory of this nonlinear dissipation and showing some examples. But we are actually building examples where we are building systems in the lab where a laser saturates due to nonlinear loss, and then examining the quantum fluctuations of the light. So yes.
Okay, so in a laboratory, the only time you see a photon is when it's terminated. Is that correct?
Yeah, when it leaks out. So indeed, there is a linear relationship between the field on the outside and the field in the cavity, this input-output relation, which lets us determine the statistics of the cavity from those of the output field.
Right, but every time you're using the word field, you're really talking about a mathematical model construct where you could say it exists like an electric field. You could have a test charge, and a gravitational field, you could have a test mass, but it really is a mathematical construct, is it not?
Sure. I would agree with that. And then it has the physical implication that its value should be related, for example, to the motion of the test charge.
Okay, so therefore, when the photon is produced, I just want to see in your mind, because as you well know, optics is very much split between EM thinking people and quantum thinking people, just like it's separated from the original, which was ray thinking people. Okay,
yes.
So optics is that very strange field. So basically, in your mind, does the photon that you're dealing with, does it get produced only because a charge somewhere is accelerating?
Yeah, so when I think about the photons that are produced, I think about it as occurring due to an oscillating dipole associated with the gain medium. So I suppose the short answer is yes. But in the quantum mechanical sense, where this is transition dipole moment between the 2 states, that acts as the accelerating charge.
Right. So the QM deals strictly at the state level, but if you want to envision it slightly EM-ish or slightly charges, you really have to have an accelerating charge to produce this phenomena we call a photon.
I would say, yeah.
Okay, because of course the photons you're dealing with, particularly at green or whatever, are like 10 to the minus 6 meters, 10 to the minus 7 meters, which is 10,000 times the size of any atomic solid matter that you would be dealing
Indeed.
with, such as the cavity.
Yes.
Okay, and so and the last one, and that is when the photon is terminated, meaning you go and measure it, can we likewise say that the same thing is going on, that the termination of a photon is an event where a charge is accelerated or deaccelerated? But it's in other words, the same kind of process, namely an accelerating charge that produces a photon or generates it or begins it, is the same process in reverse that by which you detect it or you end and terminate that photon.
Yeah, this is definitely an interesting question, and I should think about it more. My sort of naive way of understanding these things is that, well, when I detect a photon, I'm absorbing it. You know, if I detect with a photodetector, that's due to some absorption event, which is in fact associated with the acceleration of a charge.
Okay, we should probably talk offline. The
Yeah, I would
photo,
love.
the
Yeah.
neophysics one I did 2 years ago has evolved quite a bit since then. Okay, great. Thank you so much.
Yeah.
Yeah, so that sort of gets to you know, our fundamental one question we have is, what is light before, you know, what is the EM before we interact with it, right? Is there, how do you do you have a conception of that, Nick, yourself? Because the only thing we know about light, of course, is the way it interacts with our detectors, or, you know, what do you have a conception of it before we interact with it?
It's hard. Yeah, I mean, it's hard to say because it also depends. You know, that I think one of the interesting things that makes this field particularly subtle and tricky is that our interpretation largely depends on the gauge we use to analyze these kinds of fields. So, for example, you know, a classic example of this is when you think about something like spontaneous emission of an excited charge. Well, is that due to vacuum fluctuations, or is that due to the back reaction of the emission on the charge? Well, that depends on the ordering scheme you use for operators. Under one, it's purely vacuum fluctuations. On the other, it's radiation reaction, and in the other, you have two effects in unison. And so it becomes, and you know, in very much the same way, when we think about what is the fluctuations of light, you can have the interpretation that has to come from a detector somehow, but there's also evidence that light has its intrinsic, you know, you could use the fact that light can be less noisy than the shot noise level to say that light has intrinsic fluctuations, but at the same time, these are a little bit matters of details. So I think that's kind of my answer. It's pretty complicated.
I think one very telling notion in this whole field of optics, by the way, some of our interns are over at the University of Rochester, which is one of these strange places. There's only one other place in Arizona and one in China that really studies optics from every which way and has unbelievable laboratories well beyond MIT, Harvard, Stanford, and so on. It's a very interesting thing to know about, that such optics places exist where ray, EM, and quantum all co-exhibit at the same place. At any rate, is that we're using this totally Newtonian primitive word light. Light came from the tiny part of the spectrum that was visible to our eyes, like green light, red light. We see it. And the very fact we're using light versus photons, and then we lapse into EM, and then we lapse into states, and so on. It just shows you the incredibly nebulous, imprecise way this whole field is developed.
Oh, I definitely agree.
Imagine using the word light. It's like I'm trying to think of the word we'd use instead of gravity, you know, apple faller, an apple faller.
Right.
Oh, sorry, I was muted. A question about Nick, do you think we could induce a Fock state in a Bose-Einstein condensate?
It's a good question. We thought about using, those kinds of nonlinearities that you can get in those systems. Like there are these slow light systems associated with Bose-Einstein condensates that have very strong nonlinearities that we thought could maybe do the job, but there also are some subtleties associated with this. So the answer is maybe. It's very much worth investigation using big electromagnetically induced transparency and slow light phenomena.
Yeah, that would be very exciting. Yeah. So yeah, I see this one, you know, you said you're building it in the lab and doing some fun initial tests, but I think that this work is going to find a lot of applications, you know, once it's turned into engineering. So yeah, thank you very much for sharing with us.
Of course. Thank you very much for the invitation.